All right, so another way to approximate area under the curve. So let's look at a quick sketch here and look at our options so far. So we talked about a few different options. We have making a whole bunch of bars that hit on the left side, look kind of like this. Let's say that's hit on the left side. We have the option of making a whole bunch of bars that hit on the right side. That would look like that. And you can see how those would either overestimate or underestimate by quite a decent amount. Or you can make bars that hit at their midpoint. So we look at the center part, and that's where it kind of would make the bar. And that's kind of good because you have this overestimate here, you have this underestimate here, and they kind of cancel each other out. And the last type of way that we can make a approximation, or one of the last ways that we'll discuss in this course, is to make a trapezoid. So this ends up being flat. And if you look at that trapezoid, and again, not a perfect drawing here, but if you look at that trapezoid, look at how good of a job it does at approximating that. I mean, of course, there might be some trapezoids that are better than others. If this curve was a little more curvy, you might notice that trapezoids aren't always perfect, right? But they do a pretty good job. So here's another trapezoid here. Okay. And they pretty much do a good job of approximating the area. Sometimes they cut off this top and they overestimate a little bit. Sometimes if the graph is looking like this, the trapezoid might be a little underneath. So we're making all these trapezoids that are on their sides, basically. So that is today's topic. So the first thing we need to understand is the area of a trapezoid. And the area of the trapezoid is base 1 plus base 2 divided by 2 times height. And what do I mean by that? Well, we basically need to take a normal trapezoid, okay, and what do we call this base 1? We call this base 2. This would be the height. Now our trapezoids, for this sake of argument, are not really like this. They are on their side. So we're dealing with trapezoids that look like this. And the heights are actually the widths of the trapezoid, so we've got to be aware of that. But really what you're doing to find the area of a trapezoid is you're taking the average of the two bases, so you're adding up the two bases, dividing by 2, and you're multiplying that by the height. Okay? So sometimes trapezoids are really helpful. A table of values is one situation where you'd really probably want to use the trapezoid rule. So let's get right into it. So find a trapezoidal approximation for this integral for n equals 4 and n equals 8. So what does this mean? Well, this right here, the integral from 0 to pi of sine of x dx, is referring to the area that is under the curve, inside of the sine curve, and the x-axis. This is that area, okay? That integral represents this area. Now we want to approximate this area. We're going to do that with a bunch of trapezoids. So let me just draw a couple of trapezoids. I'm going to erase this area. So this is the area inside there, that red area. We want to draw some trapezoids, and let's just do that for 4 of them. So here would be a trapezoid. There's another trapezoid. Here's a trapezoid. And there, okay? So these are our different trapezoids. 1, trapezoid 2, trapezoid 3, and trapezoid 4. So let's talk about that. The smartest thing to do here is to figure out the heights of these trapezoids. So let's look at all the things that matter here. We care about when sine is 0, and we care about when sine is, well, let's look at a couple of these options. Here we have sine, what is this x value? This x value is pi, right? Sine of pi is 0. So we have the x value of pi, we have pi over 2, we have pi over 4, we have 3 pi over 4. Those are the x values we care about because they're making up our trapezoids. So we care about these things. Okay, that's a pi. And we care about the y's for that, basically. So let's just do a little bit of our math here. Sine of 0 is 0. Sine of pi over 4 is 1 over root 2. sine of pi over 2 is 1. Sine of 3 pi over 4 is, so that's going to be 1 over root 2 again. And sine of pi is 0. So these are all these values. So let's start talking about trapezoids. Let's talk about our first trapezoid right here, trapezoid 1. Okay? So that's T1, trapezoid 1, and that's going to equal the height of that trapezoid. Well, the height of that trapezoid is the width of that trapezoid because it's on its side. So the height of that trapezoid is actually going to be pi over 4. This distance here is pi over 4. So it's going to be pi over 4 times, and now we're going to average the bases and divide by 2. We're going to average the bases. So we're going to add them and divide by 2. So what is the base of this? Let's look at this trapezoid again. It kind of looks like this, actually. It's really a triangle, isn't it? So I guess this base is just 0, and this base is whatever that y value is for pi over 4, 1 over root 2. Oops, 1 over root 2. It's this one. So we're going to add those, which is just going to give us 1 over root 2 divided by 2. That's the area of the first trapezoid. Let's look at the second trapezoid. Well, all of these trapezoids are going to be pi over 4 wide, so that's a good thing. Simplifies a little bit of our algebra. And then they're all going to be divided by 2, right? And we can see that we're kind of doing some repetitive stuff here. And I'm going to try to make that less repetitive as time goes on. And now we can just talk about our next trapezoid, which is T2, this guy right here. So what's this height? Well, this is the same height that we had earlier. And then what's this height? So really we're looking at this y value and this y value for our two bases, which are our heights. Remember, it's on its side. So we have 1 plus 1 over root 2. So 1 plus 1 over root 2. That's our next trapezoid. Third trapezoid, let's look at that one. I'll use black. That's this trapezoid here. Okay, this area right here. And if we talk about the base of that or the height of that trapezoid is pi over 4, that's this distance here. Remember, it's on its side. And the bases are the two heights. So the height of the first part there is 1, and then the next height is 1 over root 2, again. And we can kind of see the pattern, 1 over root 2 plus 0 in this case. So you just crunch all of those and find out what the area is on the curve. So perhaps you could try that for n equals 8. So take a little bit to at least set it up. Maybe not do all the math out. Maybe you could find a shortcut to do a little bit less here. Because if you notice this, I'm noticing that this value is always used. And then I'm noticing that, well, this is always divided by 2. So maybe you could shorthand this when you try it for n equals 8. So give that a shot, take a few minutes, and we'll take it from there. Okay, so when you add all of those up, give me 1 second to tell you exactly what that area is going to be. Okay, so that whole integral, this, right here, the integral from 0 to pi of sine of x dx is equal to 2. So I'm hoping that when we did my approximation, we got a number close to 2. Okay, and if we look at it, do you think that number would be a little bit less than 2 or a little bit more than 2? If you look at my work here on these trapezoids, look over here. Do you think that we would underestimate or overestimate? Because think about it, we have this curve that looks like this, and then we're drawing a trapezoid underneath it. Do you think we got under 2 or over 2? Well, my estimate should be under 2, and your estimate with n equals 8 should also be under 2, but your estimate should be a little closer because you don't have as many gaps. See these gaps here? You don't have as many gaps as I do when you do n equals 8. 8 trapezoids. So maybe you came up with a shorthand method. This is the trapezoid rule. If it's a continuous function, what they're saying is that you can just take the divide by 2 out, right? And then what is this b minus a over n? That's the rest of this, b minus a over n. Well, that is really, if you're talking about something that starts at a and ends at b, and there are n trapezoids, right? If you take b minus a, let's say, for example, b minus a, well, let's say a is 1 and b is 4. Well, what is b minus, a is 1 and b is 5. Well, then b minus a is 4. It's the distance. It's the whole change on the x-axis. And if you divide that by the number of trapezoids, so you have 4, but you want to have 8 trapezoids, then they're each going to be 1/2. If you have a distance of 4 and you want to have 10 trapezoids, they're each going to be 2/5 wide. So you divide by the number of trapezoids. So that is where this is coming from. That's actually the height of the trapezoid. Height. And this 2, that in blue, is the 2 from the formula. You're averaging the bases. And now what's happening is you're noticing that when you do the trapezoid rule, I'll show you. Let me get rid of some of this stuff. When you do the trapezoid rule, and you look at a curve like this, and you start here at this value, and you end up here at this value, well, what do you notice when you're drawing this trapezoid? Well, you have this trapezoid here, and then think about it, you double count this value. You use this value again to go here, right? And then you double count that value again. You're doubling up on this value, right? And then you go down. And then you're going to double count this value. So all these ones that are in the middle, you're going to double count. So if you look at these guys, they're all doubled. You're using them for 2 different trapezoids. But here is just a single. You don't need to double it because it's not shared on the other trapezoid. It's just its own thing. So what's happening here is that you notice in the formula, you're doubling all the ones in the middle. And this is just talking about, you plug in the x value, you plug in the next x value. But you're doubling them all, but you're not going to double the first one or the last one. Okay? You're not going to double the first or the last term. Because remember, they're singletons. They're by themselves, they don't share a side. Okay. Let's get rid of some of those confusing arrows. And let's see if we can do one more example. See how we're doing on time. Okay, we're going to continue this in the next video, so take it from there.